All right, this is 6.3, matrices and systems of equations. Yesterday we talked about a system of equations and solving it using three techniques. We said that you could solve a system by graphing it. We said you could solve a system by the substitution method, and that you could solve a system by the elimination method. And we showed you examples of all three of these, and each one has its pros and cons. And so we may have had a system like this, 6x plus 2y equals 4, and 10x plus 7y equals negative 8. And what I'd like to do is solve this using the elimination method. So the first thing you have to decide is what variable do you want to get rid of?
Y.
X or y, and you say y. Okay. So if we're going to get rid of y, we're going to take our top equation, and we're going to multiply that top equation by 7. And we're going to take our bottom equation, and we'll multiply that by a negative 2. And now if we solve this, our y's intentionally cancel each other out. They intentionally go away. They are eliminated. And so when we add these up, we'll get 22x equals 44. We then divide both sides by 22, and we get x equals 2. Remember, this is only half of the solution. We need the y coordinate as well. So we're going to take this x equals 2, and we're going to back substitute it into first equation. So we're going to say 6 times 2 plus 2y equals 4. 12 plus 2y equals 4. 2y equals negative 8. Y equals negative 4. So our ordered pair is 2 comma negative 4. What's important about this whole entire process, the one thing that we want to sort of extract in its purest form, is this idea. Multiplying the top equation by 7 and multiplying the bottom equation by a negative 2. That move is very important. All the x's and y's are important too, but it's that process of saying, let's take this equation, multiply it by something, get a new equation. Let's take the second equation, multiply it by something, get a new equation, and then add them together so things cancel. Wouldn't it be nice if there was a way that we could do this process but faster, without all the x's and y's? Well, that's where matrices come in. So here's our original system. This is the same problem that we just did, the same numbers. And we can express this as a matrix. So what you've essentially done is taken this system of equations and you've rewritten it almost like in an Excel spreadsheet where you have rows and columns. So this is row 1. That's the first equation. This is row 2. That's the second equation. And this is your x column. This is your y column. And this is your number column. Sometimes you'll see a line in between the variables and the number, and that line usually represents an equal sign. If you look at where the equal sign is, that's represented by a dotted line. So what we've done is we've omitted the variables and replaced the equal sign with this vertical line. Let's talk a little bit more about matrices and how they behave. A rectangular array of numbers such as this one is called a matrix. This matrix is called augmented matrix because it contains two things: a coefficient matrix, and it also has a second half, which is what the coefficient matrix is equal to. That's the constant terms. And from this, you could write the equation of this line. So be able to go back from matrix notation to equation notation, and equation notation back into matrix notation. The row of the matrices are horizontal. So this is row 1, which is really equation number 1. And this is row 2, which is really equation number 2. And the columns are vertical: x, y, and the number. This matrix has 2 rows and 3 columns. And so when you talk about the order of the matrix, you would say this is a 2 by 3 matrix. You always list the rows first, followed by the columns. This little x does not mean multiply. It means 2 by 3. Just like when you see this on the side of a truck. What do you say? 16! No, it's a 4 by 4. If you have a matrix where the numbers are the same, in other words, if you have a 3 by 3 matrix or a 4 by 4 matrix, those are said to be square matrices. And you can see why they call it a square matrix, because when you make the matrix, it actually looks like a square. The one that we have displayed here is called a rectangular matrix. These are the operations we can do with the rows of a matrix. And we're going to use all three of these. Number one, you can interchange any two rows of a matrix. Number two, you can multiply each entry in a row by the same non-zero constant. And if you remember, way back up here, that's what we did when we took the first equation and multiplied it by 7. That's how we got the 42, the 14, and the 28. So as long as we multiply everything by the same number, it's cool. Rule number 3, add a non-zero, blah, 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 blah. How about if we just say you can add one row of a matrix to another row? Did we do that with equations? Sure, we did that with equations. Right here. We took this equation and we added it to the second equation. And we added it with purpose, negative 14 and positive 14, but we still added them. So everything that we did here with equations, we're now doing the same rules, but they're no longer in equation format, they're in matrix format. We can use these three rules on an augmented matrix to solve the system. First thing we're going to do is we're going to convert them into matrix format. So you're just going to grab the coefficients of x, y, and z. You're just going to throw them in a matrix. There you go. Step number 2 is we want our matrix to look like the matrix on the left. See this matrix on the left? And I've written here, I've written this matrix a couple times to remind you this is our goal. What we want is, the important things of this matrix are, and we'll talk about what this matrix is called in a little bit. We want a diagonal of 1s, and then what we would like to have are zeros to the left and below that diagonal of 1s. And if you think about what this says z equals f. And then you could take that and figure out what y is equal to. And you could take that and figure out what x is equal to. Remember, because this is x, y, and z. So our goal is to take the matrix that we're given and using those row operations, rewrite it in this format. It would be really nice if that top row of numbers began with a 1. And so our first move is we're going to swap these two rows. Swap row 1 and row 2. Step 2, we would really like this 2 to be a 0, because that's what the template shows off to the left, right? There's a 0 there. And so how could we make that a 0? Well, what we're going to do is we're going to take and multiply the first row by a number that when added to the second row makes it a 0. And you can kind of see it's written down here. This is what we're going to do. If we take our first row and we multiply it by negative 2, and now I'm going to take this row and I'm going to add it with the second row. Negative 2 plus 2 gives you 0. 6 plus negative 1 gives you 5. 4 plus 1, 5. 2 plus 8, 10. So now we have this new row, a new row number 2, and the new row number 2 has a 0 as its lead term. We're going to do the exact same thing with row number 3. So we're going to take our first row, instead of multiplying row 1 by a negative 2, what do we want to multiply to get rid of this positive 4? Multiply by a negative 4. So we're going to say negative 4 times 1, negative 3, negative 2, negative 1. 1 times negative 4, negative 4. Plus 4, 0. Negative 3 times negative 4 is 12. Plus 0, 12. Negative 2 times negative 4, 8. Plus 5, 13. And negative 1 times negative 4 is positive 4. Plus 23 is 27. Now what we'd like to do is we would like to take the second row and make it a positive 1. So we're going to take the second row, divide everything by 5. So 0 divided by 5 is 0. 5 divided by 5 is 1. 5 divided by 5 is 1. 10 divided by 5 is 2. So now our first row has the 1. Our second row has the 0, 1. And now we need to move on to our third row. So boy, it really would be nice if this was a 0. And so we're going to take row number 2 and we're going to multiply it by negative 12, which is going to give you a new matrix. 0, negative 12, negative 12, negative 24. and take that and add it to this row number 3. So 0 plus 0 is 0. Negative 12 plus 12, 0. Negative 12 plus 13, 1. And negative 24 plus 27, 3. So now we have our matrix in this 1, 1, 1. We've got a diagonal of 1s. And we have 0, 0, 0. Z equals 3. So this is from row 3. Row 2 says 1y plus 1z equals 2. Or in other words, y plus 3 equals 2. Y equals negative 1. So we've got z equals 3, y equals negative 1. Now let's go to row 1. Row 1 says 1x minus 3y minus 2z equals negative 1. X equals 2. So your ordered triple is 2, negative 1, positive 3. And here's how you set up things in row echelon form. Number 1, if a row does not consist entirely of zeros, then the first non-zero element must be a 1. Number 2 says, for any two successive non-zero rows, the leading one in the lower row is farther to the right than the leading one in the higher row. Rule number 3, all rows consisting entirely of zeros are at the bottom of the matrix. So if we did have a fourth row and it was all zeros, you have to put that at the bottom. There's then a fourth property, which says if you have zeros everywhere, 0, 0, 0, 0, 0, 0, except for this diagonal of 1s, this is called reduced row echelon form. So it's incredibly easy to read off your answers from this matrix. Is A in echelon form? Yeah, it's in echelon form. The first number in each row is a 1. There's this, diagonal where it's farther to the right, and everything looks good. What about B? No, because it's got that negative 2 there. So, sorry B, you are not in echelon format. What about C? This row has to be down below. So this is not in row echelon form. And D is extra cool because it is in reduced row echelon form. This is called Gauss-Jordan elimination, which is basically the same thing we've been doing. And so we're going to run through this example using Gauss-Jordan elimination. And basically what you're going to do, when we did this Gaussian elimination, we made our way from the top and we worked all the way down to the bottom. Now what we're going to do is we're going to start at the bottom because we've got our zeros in there, and we're going to work our way back up to the top. Here's our original matrix, and from this one you could say, yeah, okay, z equals 3. You could plug that in here and solve for y, then you could back substitute into here and solve for x. But what we're going to do is we're going to use the Gauss-Jordan elimination to work our way back up. We're basically doing the exact same thing we did on the way down, but now we're working our way back up. So you're going to take this 1 and this 3, and you're going to say, boy, I really would like to get rid of this 1. I wish that was a 0. So we're going to take this row, we're going to multiply by negative 1, and then add it to row 2. And that's going to create a new row. Then we're going to take that, and we're going to add it to row 2. So 0 plus 0 is 0. 1 plus 0 is 1. 1 plus negative 1 is 0. And negative 3 plus 2 is negative 1. You then do the exact same thing with row 1. So what we're going to do is we're going to take our row and we're going to multiply everything by 2. We'll take row number 3, multiply by 2, and add it. 0 times 2 is 0. 0 plus 1. 0 times 2 is 0, plus negative 3, negative 3. 1 times 2, 2, plus negative 2, 0. 3 times 2 is 6. 6 minus 1, 5. Now we're going to take row number 2 and multiply everything by 3. 0 times 3, add it to 1. 1 times 3 is 3, plus negative 3, 0. 0 times 3, 0, plus 0, 0. Negative 1 times 3, negative 3, plus 5, 2. And now you have reduced echelon form of the matrix. What is x equal to? 2. What's y equal to? Negative 1. What's z equal to? 3. So your ordered triple is 2, negative 1, positive 3. If you end up with a matrix that has all zeros on one bottom row, this is same line. Because if you interpret this, it says 0 equals 0. And we said anytime when you're solving an equation you get 0 equals 0, that means that these are the same line and that there are infinite solutions, or all real numbers. If you're solving a matrix and you get a row that looks like this, this is equivalent to saying 0 equals 9. And when does 0 equal 9? Never. When do these lines intersect? Never. They are parallel lines and they never intersect. So this is DNE, no solution.